We are now going to define how to integrate a top degree form on a manifold. More precisely, we will be considering an n-dimensional smooth oriented manifold and an n form on that manifold, and we will define how the integration of that n form on that n manifold. Now, there are two approaches to do this. One is to use the classical Riemann integral and what is known as the partitions of unity. Two is to use the nice properties of the Lebesgue integral to achieve this integration process in a concise and elegant manner. As expected, I am going to take the latter approach via the Lebesgue integral. If you are not familiar with Lebesgue integrals in Rn, do not worry. After I give the proof of Stokes theorem, I'm going to take a brief, I'm going to give some lectures on an elementary approach to the Lebesgue integral, the so-called Ries approach to the Lebesgue integral, and I will be proving the key theorems like the dominated convergence theorem and the change of variables and Fubini's theorem, which will all be used in the proof of the well-definedness of the integral as well as the proof of Stokes' theorem. So just wait a few weeks and I will be uploading videos on the Lebesgue integral. You can watch, you can resume watching these lectures once you watch that. Okay. So let us define the basic things we need from Lebesgue integral theory. Let us write those down so that you have a convenient reference. This will be a refresher. So we have, so the essential fact that I need is we have a unique translation invariant countably additive complete measure defined on the Lebesgue sigma algebra on Rn. So the Lebesgue sigma algebra will contain all open sets and closed sets. By definition, it is the sort of the completion under the construction of the Lebesgue measure of the Borel sigma algebra. Okay, we will denote this measure usually by dx. This measure by dx. Okay, so the set of Lebesgue integrable functions, these are functions whose absolute value is integrable on Rn, is denoted L1 of Rn. Okay, and this is a vector space. We have a seminorm on this vector space given by f going to integral of f mod f dx. Okay, now this is a seminorm. Seminorm means there are functions other than the zero function for which the norm is 0. As you are familiar from Lebesgue integral theory, whenever two functions agree except on a set of measure 0, that is if f and g are almost everywhere equal, then their integrals are the same. Therefore this will just be a seminorm. Okay, now I'm going to state one of the central results of Lebesgue theory, which is Lebesgue's dominated convergence theorem. And this is going to be extensively used in the proof of well-definedness of the integral. Let fk be a sequence of Lebesgue integrable functions, such that mod fk is less than some function g, and this g is also Lebesgue integrable. Okay, if this fk converges to some f almost everywhere pointwise, then f is Lebesgue integrable, and as you expect, integral of fk converges to integral of f. Okay, so this is one of the central facts. This is what makes the Lebesgue theory so much more convenient than Riemann integrals. You have nice behavior under convergence. Now I'm going to define integration of a function not necessarily on the whole of Rn. Now suppose f is from S to R, where S is some subset of Rn. Okay, and suppose omega is a subset of S. We define this new function f subscript omega of x to be by definition equal to f of x if x is in omega, 0 otherwise. So this function f omega is a function from Rn to R. Okay, now we say f is integrable on omega if f omega is integrable on Rn, of course, integrable on Rn. And we also set integral over omega of f to be by definition integral over Rn of f omega. Natural and straightforward definitions. Now the second major theorem, this theorem is also true for Riemann integrable functions, but I'm going to state it for Lebesgue integrable functions, and this is going to be crucial in the proof of the well-definedness of the integral. This is called the change of variables theorem. The change of variables theorem. What this states is the following. Let omega subset of Rn be open and f from omega to R be integrable. Let G U subset of Rn be another open set, and G from U to omega be a diffeomorphism. Okay, C1 diffeomorphism. C1 is enough. Then this function f composed with G modulus of determinant of dg is integrable on U. This is the first conclusion. And the second conclusion says the integral of f on omega is nothing but integral of f composed with G modulus of determinant of dg on U. Okay. Now in the ideal circumstance, if G were to preserve volumes, you would not expect this determinant factor. But because in general G could distort volumes, we need to make a correction factor when we pass from an integral on omega to an integral on U, and this correction factor happens to be the determinant of the Jacobian matrix with an absolute value, of course, because in general the determinant is going to give you the signed volume. To take into account that, we need to do this. Later in the course, I will give you a very elegant recent proof of this change of variables when I cover Lebesgue integrals using the elementary approach. There's a lot of geometry behind it. If I feel motivated enough, I'll give you a geometric proof as well. The actual classical proof of this is quite involved and complicated. You will have to do a very fine-grained analysis of how volume is distorted and all that. But it's worth seeing once, even though it's tedious. Okay, now we have all the tools ready to define integration on manifolds. So let me make a global remark for the rest of this course. Henceforth, henceforth all manifolds will be orientable and smooth. We will cover orientation covers. We will consider orientation covers that are all compatible. What I mean by that is, if you are given an orientable manifold, as we have discussed before, there are precisely two orientations possible. We once and for all, throughout the considerations, we will fix an orientation on the manifold, and we will only consider those orientation covers that respects this orientation. In other words, if you take a particular local parameterization phi from U to M, coming from this orientation cover, I expect d phi E1, d phi E2 dot d phi En to be equivalent to the given orientation. Of course, this must be taken at some point A. This must be equivalent to the orientation of that particular tangent space at the point phi of A given by the orientation. So I will only consider compatible orientations. Okay, so one more final definition we need. We say A subset of M is small if A is in the image of some parameterization. Okay, so now we can go ahead and define integration on manifolds. First, we define what measurable sets and sets of measure 0 are. This is the definition will be rather straightforward. Measurable and sets of measure 0. Measurable sets and sets of measure 0. A set A subset of M is said to be measurable if phi inverse A is measurable for all parameterizations phi. No matter what local parameterization phi you take, the pre-image under this parameterization of the set A should be measurable. Sets of measure 0 are defined analogously. Sets of measure 0 are defined analogously. You can check for yourself that when you take the set of all measurable functions on a given manifold, that will turn out to be a sigma algebra. However, just given the manifold with the current theory we have developed, we have no natural way to give a measure on the sigma algebra. Okay, now the crucial fact we are going to use to define the integral is to decompose the manifold into a disjoint union of small measurable sets. So the claim is that any manifold can be decomposed into a disjoint union of small measurable sets. And this is not so hard to show. Just consider phi I from Ui to M, an orientation cover, set A1 to be just phi 1 of U1. Of course, A1 is going to be measurable. You can check that easily. Then A2 is going to be phi 2 of U2 minus A1 ... AR is going to be phi R of UR set minus union I equals 1 to R minus 1 AI, and so on. Okay, so you can recursively define these sets AI, and it is clear that each AI is small and each AI is measurable, and AIs are pairwise disjoint. Now, the idea behind the integration process is very simple. We are going to break up the manifold into these pairwise disjoint small measurable sets. There might be a gazillion bazillion ways to do that, and we are going to fix one such breakup of the manifold, and we are going to define how to integrate on the manifold by summing up over the integrals on each one of these small measurable disjoint sets. The crux is that it really doesn't matter how you break up the manifold, the answer you get will be the same. And that's the place where orientation plays a key role. So what I'm going to do is I'm going to state this theorem. It's going to be at least 2 slides long, hopefully not 3. And then in the next video, we are going to sit down and prove the thing. Surprisingly, the proof is not substantially longer than the statement. So let's state the theorem. Theorem, definition of the integral on a manifold. Okay, let M be a smooth manifold of dimension n. Of course, I'm suppressing some global conventions. It's going to be an oriented manifold, which I already remarked. Smooth manifold of dimension n. Let me just put it here for completeness. Of dimension n, and omega be a top degree form. Let AI and BI be covers of M, be orientation, no orientation cover, sorry about that. Let AI and BI be covers of M by small measurable disjoint subsets. So by disjoint, I mean that AI and AJ are disjoint and BI and BJ are disjoint. AIs and BJs could intersect, of course. And let phi from ui to m and psi I from psi j from vj to m be orientation covers with with AI subset of ui and bj subset of vj. So I should change this index to j. Okay. Now the fact that if you are given these covers AI and BI by small measurable disjoint sets, then you automatically get orientation covers phi and psi j such that this happens. One second, I have made a slight mistake. This is phi. Of course, it cannot be in ui psi j of vj, because AIs and BJs on the manifold and ui and VJs are on Euclidean space. There was no way that the previous thing could have been true. Of course, it's possible because our manifold could also be in Rn. So anyway, coming back to this, the central part. Given small measurable disjoint subsets, I want you to sit down and show that there will be orientation covers phi and psi j whose images in fact contain AI and BJ respectively. Okay, so this is always possible. I want you to check that. Okay, now we are going to make several assumptions about what is happening. Assume first condition, on each ui the local coordinate of the form say omega I. So better it would be to write on each phi of ui Okay, each phi I of ui will be even better. On each phi I of ui, this looks like a 1, so let me fix it. On each phi I of ui, the local coordinate of the form, say omega I. What I mean by this is, this phi I is going to give you a frame field on ui. This is a top degree form, so the dimension will be 1, so there will be only one coordinate function which I am going to call omega I. So the local coordinate function on phi I of ui with respect to the chart phi I, not the chart, with respect to the local parameterization phi I is called omega I, is such that omega I composed with phi I is integrable on Ci, which is by definition phi inverse of Ai. Okay, so I will draw a picture towards the end so that you are not utterly confused. 2, the summation over I integral of Ci omega I composed with phi I modulus is less than infinity. So this converges. Then we have in fact three conclusions. On each phi j of Vj, the local coordinate of omega, say omega j, is such that omega j composed with psi j is integrable on dj, which is by definition psi j inverse of aj. 2, the sum over j integral over dj modulus of omega j composed with psi j is less than infinity. Okay, converges. That means number 3, the integrals with respect to both partitions ai and bj coincide. What this means is summation over I integral of Ci omega I composed with phi I is exactly the same as summation over j integral over dj omega j composed with psi j. Okay, so it doesn't matter which partition via small measurable disjoint subsets whose union covers M you choose, you will get the same value for the integral. So let's draw a picture of what is going on, otherwise we will be completely lost. So we have this manifold, and what we are saying is we are going to break up this manifold into small measurable subsets. So I'm just going to arbitrarily draw some stuff, and this is going to be the breakup. We have several regions. These are all supposed to be small measurable subsets. Okay, so roughly there seems to be around 10 of them in this picture. Now how the integral is defined is, take one of these small measurable subsets. This is going to be contained in some cover. Let's just say phi 1 of u1, let's say for concreteness that this is contained in phi 1 of u1. Okay, now since this first portion is contained in phi 1 of u1, this differential form top degree from omega will have an coordinate with respect to the frame field given by d phi 1 e1 dot 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 d phi n en. That will form a frame field on phi 1 of u1. So what you do is call that omega 1. Then the hypothesis says that omega 1 composed with phi 1, this is phi 1, omega 1 composed with phi 1 is integrable on u1. That is the hypothesis. And we also have that when you take the absolute values of these omega I composed with phi I and take their sum of integrals, then you get a finite value. So if you sum up the absolute value of omega 1 composed with phi 1 integral on u1 plus omega 2 composed with phi 2 on u2, let's say, and you sum up all of these, sum up these 10 terms together, you get a finite value. Of course, here since the manifold is already broken up into a finite number of pieces, there is nothing substantial happening, it will always converge. But in general, a manifold need not admit a partition into just finitely many sets. That may not always happen. In that case, it will be a countable sum, and convergence issues have to be dealt with. So the hypothesis is that in one particular breakup, on each piece the local coordinate of the form is actually integrable, and the sum of the integrals, the sum of the absolute values on all these sets put together is actually a finite quantity. Now what the conclusion of the result says is that it didn't matter. The moment you have one such partition for these nice things happen, it happens for any other partition. So if I were to have chosen a different partition of the manifold, some other different partition, I'm just drawing random stuff to get a partition. So suppose I had chosen a different partition, then the local coordinates with respect to this, each one of these sets are small, so each one of these sets is going to be contained in one image of a parametrization, each one of them. Then if you look at the local coordinates of the form omega under those, and you consider the integral, it will still be absolutely integrable. The absolute value will be integrable. And not only that, the sum of the absolute value integral, sum of the integrals of the absolute values will still converge. And not only that, the integrals, the sum of the integrals with respect to both partitions will give you exactly the same value. So in essence, we have shown that there is a well-defined integral of this top degree form on this manifold. So what we will essentially do is we are going to write down the expression for the integral in terms of the intersections of these two partitions. That is, you take these AIs and BJs and intersect them and look at what happens there, starting with the assumption that integral of omega j composed with integral of omega I composed with phi I, the absolute value of that is integrable, and try to transform it to integral along the VI's, or rather the VJ's. So there is, at that point, we need to apply the change of variables. Okay, so this is the brief intuition and the precise statement of integration on a manifold. In the next video, I'm going to actually sit down and prove that the integral is well defined and all the properties claimed 1, 2, 3 is in fact true. This is a course on real analysis, and you have just watched the video on the definition of the integral on a manifold.